Let's spend a little time talking about ways we can optimize our array list ideas. So to get there, I want to reflect on why we built the array list in the first place. There was something about a linked list that they just weren't very good at. Do you remember what it is? Okay, it was that getting items from the middle of a list is slow if it's implemented as a linked list, because you have to scan to the middle of the list. That was the main motivation for building the array list. Well, now that we built an array list, we should think back. Are they just better? Is there something that a linked list is better at? Think about that for a sec. Okay, indeed, there actually is something that a linked list is better at, specifically front operations. Imagine adding to the front of an array list. You now need to move everything over one. Or if you remove first, you now need to move everything back one. There's also a smaller concern that might have occurred to you, which is that sometimes array list operations incur a resize, because you have to double the size if you get too full, or quarter the size if you get to, or sorry, I should say half the size if you get to empty. And by the way, it doesn't really matter like exactly what multiplicative ratio. Those are just the typical ones that I used in class. But that idea of doubling or shrinking your array is going to cost something. But those operations of resizing happen so infrequently that it's basically negligible, so we don't really care that much about that. The main disadvantage, if we're just comparing them head to head, are the first operations. So back when we were designing linked lists, we had a similar problem, right? We had the fact that remove last was slow. So in our singly linked list prototype, we added this last pointer, but we found that remove was slow. So question, how do we make it faster again? Okay, so a little bit of review. Okay, we added some backwards links. We had this different layout here. By adding reverse links, it's now fast to find the second to last item and make it the new last. So drawing from that same inspiration, you might ask yourself, how could we modify our design so that front operations are fast? So if we were to add new operations here, if we have, I'm only showing the last operations here, consistent with the diagrams earlier in lecture, but suppose that we had first operations and we wanted remove first and add first to be fast, what could we change? You could actually sit down if you wanted for 20 or 30 minutes and think about what the right approach might be, or maybe less time than that, I don't know, a couple minutes. But I'll give you one approach. So the inspiration here is to think that the front of the array doesn't need to correspond to the actual front of the list. If we could use like the middle somehow, maybe something like that would work. And we'll get to that. Like that's kind of the kernel of truth. But I'm actually going to go a little wackier on you. And I'm going to say, imagine if we just had a different shaped array altogether. Let's imagine that we had an array that was shaped like a circle somehow. Okay. So if we had an array shaped like a circle, one way it might work is like this. If the user has a list that has the number 4 in it, then in our array somewhere we have a 4, and then we have a next first pointer and a next last pointer that tell us where the next first and next last should go. So if I call add first, the user's mental model is that now there's a 3 at the front. So a question for you is, how would we modify this circular array to match the user's mental model? After all, that's what data structure implementation is all about. A user has a certain expectation. I need to meet that desire however I choose. So what do I do here given this setup? Okay, so I'm going to fill in a 3 here. That's one thing. And I'm going to increment the next first pointer. Okay, I'm going to push it this way. Okay, you might call that decrementing if you want, but whatever. I'm just pushing it out. Okay. Another example, let's say we do add last 5. Well, in that case, the user is imagining that this list I have, this abstract object 3, 4, that it now has a 5 at the end. So how do we affect this actual circular array? How do we change it? Okay, we increment this next last pointer, and then we change this value to a 5. Okay, or maybe it's better to say it the other way around. We put the 5 where next last used to point, and then we increment next last. Okay, so that's the idea of a circular array. If we now call remove last, try and just think in your head, what will this look like? Okay. So again, we move next last up. And if we call remove last again, now we're left with just 3. And you can imagine as you're calling add first and remove first and add last and remove last, that you're going to be just scooting around this array. And it doesn't really matter where exactly in the array you are. It may be that the one item array of 3 is here, or the 3 could be there, or could be there, as long as the appropriate next first and next last pointers are set up matching the expectation of the user. So to really test your understanding and give you a little bit more texture for this, let's suppose that our circular array looks like this. We have our next first pointer here, next last pointer here, right next to the 4. Try and think, what is the user's mental model? Like, what's the list they have in their head that this circular array is representing? Try and work that out on paper. And if you're a little stuck, you can just go back a bit and look at what we did before. Okay, so remember that we were always reading in a clockwise manner, and that the first real item is always right after next first. Okay, so the array in this case, or the list I should say, is 092654, 092654. Okay, so great. We see that there's a clear mapping that given a user's mental model, we can create the appropriate actual circular array, and vice versa. Given an actual circular array, we know what the user's mental model is. One quick note, that there's actually multiple circular arrays that can represent the same abstract list. So if I go between these two examples on the slides here, where I've just rotated everything over one spot, that's fine. That's the exact same underlying abstract list. This is just, it's a different representation of the user's expectation. Okay, both of these are fine. All right, so given that we can easily convert a circular array with our eyeballs into the user's mental model, that means that in code, if we had a circular array, it should be possible to write add functions and remove functions and get functions for both ends. In fact, we could also write get in the middle. It'd be a little complicated because if I say like get me item 2, I have to start at next first and do a little bit of math to say I need to go 3 positions ahead of that. But the code's not going to be that bad. And the other good news is they'll be fast. Because this is an array, all of those operations for both ends will be really fast, and actually a get into the middle will also be really fast. One concern is if we run out of room, like all of these are full, what should we do? And the answer is, what do you think? We'll resize, and we'll end up with 16 sectors here instead of 8, where I'm calling each of these things a sector. And so that's all good and well, but there's just one minor problem, which is that circular arrays are not real. And so we'll address that in the next video.